Okay, let's talk about polyatomic molecular compounds. These, technically speaking, by definition, are compounds that contain mostly nonmetals and where you have more than two different kinds of elements. In particular, the ones that we're going to focus on are the ones that contain only three different kinds of elements, where the first element is hydrogen and the last element is oxygen. We refer to them as molecular oxyacids. And the first thing I want to show you in respect to these elements is what happens when the element in the middle, the central element, belongs to the third through the sixth row in the periodic table. The one thing that we're going to utilize to come up with the names is to account with the fact that elements below the second row of the periodic table can take up a max number of 4 oxygens. And the number of H's are actually given by 8 minus the group number of the central element. Central elements that reside in the second row, on the other hand, at most can take up 3 oxygens, and the number of hydrogens are given by 6 minus the group number of the central element. And the reason for the lower value of oxygens and the lower value here for number of hydrogens is a result of the fact that the second row elements are smaller than elements below the second row. So we can only accommodate 3 oxygens as opposed to 4. But you're going to have to keep an eye out for that maximum number of oxygens, because we're going to derive the names for these molecules based on that number. And what you can see here is a diagram depicting the full van der Waals radii of the different elements as they bind to each other. So here you can see an oxyacid starts with hydrogen, ends with oxygen, and you have the additional element in the middle, in this case phosphorus. And you can see that the phosphorus, which is presented in purple right here, is pretty much mostly occupied by all the 4 oxygen atoms. Similarly for sulfur, a good chunk of the sulfur is being occupied, and so is the chlorine. But the one thing to be mentioned is that in all of these examples, the oxygens are really not coming in direct contact with each other. There is at least a small tiny separation between them that allows them to be separate from each other. And if you look at the heavier analogs, arsenic below phosphorus, or selenium underneath sulfur, or bromine underneath chlorine, you have even more room for those 4 oxygens to be distributed throughout the volume of that central element. Now, when you look at the second row elements like boron can only take up 3 oxygens as the bigger number, and you have this overall setup where the oxygens are distant from each other. If you have 4, you could actually place a 4 there, but it turns out that the actual structure will be something like H5Br04. And if you think about it, this is technically just the same molecule we have here with an extra water molecule. On the other hand, let's take a look at the carbon analog, 3 oxygens only. As you can see, the space between the oxygens is already very minute to begin with. So if you were to put a 4th oxygen, the oxygens will start touching each other. And because of that repulsion between them, typically we don't have 4 oxygens on carbon. In fact, we just don't. And for nitrogen, similar story. Nitrogen is even a little smaller than carbon, so now you have almost direct contact between the oxygens. So putting 4 of them on nitrogen will definitely have oxygens falling on top of each other, which is not a stable situation. So the size of that central element dictates ultimately whether you have 3 or 4 oxygens. And luckily for us, what that basically means is that if the central element is on the second row of the periodic table, we'll end up with 3, but any other element below it is going to have 4 oxygens. And what we're going to do is we're going to utilize a table to come up with the names of these oxyacids, the ones that contain hydrogen and oxygen, plus some other element. What we're going to pay attention to is not only the number of oxygens, but the group number to which the central element belongs to. And the idea is that if you look at an element, a central element that is in group 7 in particular, for that element you're going to have the following rows of naming per followed by blank, and the blank will be filled by the name of the central element. So per blank-ic acid, blank-ic acid, blank ose acid, and hypo-blank ose acid. The way this gets arranged, starting with the peric acid and going all the way down to hypo-ose acid, is that it's based on the number of maximum oxygens. If your molecule has the maximum number of oxygens that it could take up, then you will name it peric acid as long as the central element is in group 7. And then as you decrease the number of oxygens from the maximum by 1 or by 2 by 3, that tells you which one of these rows you're going to take up. Now, if the central element is actually from groups 3 to 6, then you will not start with peric acid. In fact, you don't even have peric acid in the name right here. You start directly with ic acid, and then you work your way down to hypose acid, but the logic is still the same. The first row in the naming corresponds to the maximum number of oxygens, and then you just go down the list in terms of the number of oxygens that your compound may have. So depending on how many oxygens your compound actually has, you're going to be naming it in a different way or a very specific way. Alright, so we're going to derive the names for the common oxyacids that you're going to deal with in this class. But the trick that I'm showing right here applies to a vast number of compounds just the same way. Alright, so here we go. For group 7, this is the halogens. Group 7 involves chlorine, it involves bromine, it involves iodine. Alright, so what happens is that for those elements which actually lie below the second row, we expect there to be a maximum number of oxygen equal to 4. Alright, and also because we're in group 7, 8 minus 7 tells us that we're going to end up with 1 hydrogen in the compound. So right out of the gate, what we do know is that we're going to have 1 hydrogen for all of the chlorine analogs. And if we start with the maximum number of oxygens, we could have 4 oxygens, we could have 3, we could have 2, or we could have 1. And now we look at the table. Since chlorine is in group 7, we're going to use the following set of rows. The one that has the maximum number of oxygens, namely 4, is going to be called per something ic acid. The something has to do with the chlorine. So in particular, the first one will be called perchloric acid. The next one that has 1 less oxygen than the maximum, or in other words 3, will be named something ic acid, and since the something is chlorine, this ought to be called chloric acid. Okay, move on to the next one. If we have 2 less than the maximum number of oxygens, which will be 4 minus 2 or 2 oxygens, this is called chlorose acid. And then last one that has 3 less than the maximum number of oxygens ought to be called hypoose acid, or in this case hypochlorose acid. Alright, so far so good. Now the beauty of this method is that this doesn't just end with chlorine. This applies to any of the heavier counterparts of chlorine, right? So it applies not just to chlorine, but it applies to bromine and it applies to iodine. So guess what? You could literally just copy and paste what we just did right there. The only difference now is that we have bromine instead of chlorine, and the names are going to be the same. Maximum number of oxygens, peric acid. Next one, ic acid. The one after that, ose acid, and the one with the least amount of oxygens, hypoose acid. And we just fill in the name of the central element. So the first one will be perbromic acid, followed by bromic acid. Next will be bromose acid, and we end up with hypobromose acid. Alright, if we do the same thing with iodine, start with the maximum number, work your way down to 1. You will name the first one periodic acid, followed by iodic acid, iodose, and hypoiodose. And once again, this is based on the number of oxygens. Alright, now let's move further to the left. Now we're dealing with a group 6 central element. So we'll no longer use the top portion of the table here for the nomenclature. We'll use the bottom portion. And for group 6, we're going to start with sulfur. And also, because we're in group 6, 8 minus 6 tells us that we will have 2 hydrogens in the structure. Alright, so with sulfur, we have 2 hydrogens, maximum number being 4, since sulfur is below the second row. So the next one will have 1 less oxygen, or 3 oxygens altogether. Now, unlike the halogens, for the group 6 elements, you basically stop at 3. And this is kind of the part where you will have to just memorize where you have to stop, right? So you wouldn't go to H2SO2 or H2SO. Not to say that those things don't exist, but they're not common acids that we are meant to be concerned with. Alright, now in terms of the naming, since sulfur is in group 6, we stick to the bottom portion of the table, and dealing with the maximum number of oxygens, we give it the name space-ic acid. The space belonging to sulfur in this case means that the name will be sulfuric acid. And the next one that has one less oxygen than the max ought to be called sulfurous acid. Alright, now we're going to follow the same approach for the heavier congenerator of sulfur. Underneath sulfur we have selenium, maximum number 4, next number 3, so the first name will be selenic acid, followed by selenous acid, so the same logic. And if you want to include tellurium in the sequence, the same story will ensue. You will still have 2 hydrogens for this molecule because we're still in group 6. We start with 4 oxygens, go down to 3 oxygens, so the first one will be called telluric acid, and the next one will be tellurous acid, and we're basically using the table right here. Alright, let's move on to group 5. Next to sulfur, in group 5 we have phosphorus, and because we're dealing yet again with a group 3 to 6 element, we're going to have to use the bottom portion of the table. Additionally, because this is group 5, if we subtract 5 from 8, we're going to get 3 hydrogens in the structure. So we'll have to write H3, and ending with the maximum number of oxygens, we'll have O4. And at that point in the middle, we fill in the elements from the group, so phosphorus. So we have H3PO4, which if we look at the table, once again, we keep using the bottom portion because we're dealing with groups 3 to 6, in this case group 5. So the maximum number of oxygens is going to be phosphoric acid, followed by the next number of oxygens, which is one less than the maximum, phosphorous acid, and the last one, which has 2 oxygens, is going to be called hypophosphorous acid. Alright, so as you can see, the systematic way of naming these things is relatively simple when you have this table and you make use of it. Now I'm going to continue the process, and by the way, for phosphorus you're going to go down to 2, but for the other heavy cogenerators you're going to only go down to 3. So here is where the memorization comes in. But much the same way, 3 hydrogens, 4 oxygens. This is called arsenic acid, followed by arsenous acid. And if we go even further into antimony, we still have 3 hydrogens because we're in group 5. We start with the 4 oxygens, so this is called antimonic acid. And the next one will be called antimonous acid, once again based on the table. Alright, so now let's take a look at the second row elements, because that's where the story gets a little funky. For the second row elements, we can only have a max number of 3 oxygens, and for number of H's, we subtract the group number from 6. If we are in group 3, 6 minus 3 tells us that we have 3 hydrogens. And the one element in group 3 which lies in the second row is boron. So we're dealing with 3 hydrogens, 1 boron, maximum number of oxygens being 3. We are dealing with groups 3, so this starts with ic acid for the maximum number of oxygens. So this is called boric acid. Alright, moving on to group 4. Same idea. If we are in the second row, we can only have a max number of 3 for oxygen, and we use 6 minus the group number. 6 minus 4 says that we need 2 hydrogens, so we have H2 followed by C, which is the element in group 4 on the second row, and the 3 oxygens. Based on the table, this ought to be called carbonic acid. Alright, and then the next one, group 5. This is where nitrogen is located on the second row. Group 5, 6 minus 5 tells you that you only need 1 hydrogen, 3 oxygens max, so this will be HNO3. And based on the table, this ought to be called nitric acid. For nitrogen, as opposed to carbon and boron, you actually have one more identity or one more possibility, HNO2, which based on the table ought to be called nitrous acid. Alright, so these are basically all the common polyatomic acids that you ought to be aware of. But you could use the same method of naming molecules to name other molecules that contain hydrogen to begin with, oxygen ending up, and some other element in the middle. Alright, so with that, I will stop the video right here, and on the next video, we'll start talking about ionic substances.